Thanks for joining the session today. Um, I'm Jian Zhang. I'm from Intel, software engineering manager, leading a team working on optimizing the big data software stacks on Intel platform. Today, I'm going to introduce our topic, accelerating Spark for data analytics on the cloud with remote persistent memory pool. So here is the brief agenda. We will first start with the motivation and the background, why we are doing this work. Then we will give a brief introduction of a remote persistent memory, what is persistent memory, and how people typically using it, and how it can be used in different use scenario. And next for that, we will deep dive into the remote persistent memory for Spark Shuffle. We have two implementations here. One is place the persistent memory on the local compute node and accelerate Spark Shuffle remote read. The second one is extending the persistent memory to a fully disaggregated mode, so building a remote persistent memory pool. Then we will wrap up the topic with a summary. Let's take a look on the motivation. So based on our experience of the customer engagement, we observed several key changes in the data center infrastructure evolution. The first and foremost one is there is a trend to do the compute and storage disaggregation, because people were able to scale their compute and storage independently. They were able to reduce their cost and can sort of provide better utilization on all their hardware resources. And in those environments, it's typical that it's a diskless environment, and it's become more and more important. The second trend is the hardware deployed in those data centers is becoming more and more advanced. For example, people usually have like a 25 gigabit and even 40 and 100 gigabit networks in their data center. So it makes the local storage less attractive. The third trend is there were new storage products emerging, the storage class memory, the opt-in persistent memory storage stuff. But on the other hand, Spark Shuffle do pose some new challenges in the big data, in the large-scale big data cluster. First and foremost, one, people usually complain that the resource utilization is not very balanced, and usually your job match out of memory due to slow garbage collection. And if you are using traditional hard drive for the shuffling, the disk I/O is too slow. And because Spark Shuffle has a disk bill, it will further degrade your performance. And when you have more data, your shuffle I/O will increase dramatically and hurt your performance. And even if you are using SSD as a local shuffle media, it's going to be wear out because the endurance is not that very good. And for some typical workload or typical jobs, it is so long that you cannot even afford the recompute cost. So those are the typical challenges Spark cluster is facing today. Let's take a look on what Shuffle is. Basically, it's a process of exchanging the data from the mapper to the reducer. For example, the mapper will read the input data and split it to multiple splits, and then using a user-defined function to do the calculation and merge it on the local drafts. And the mapper and the reducer then will fetch the data, doing the sort, and then write to the final output. So from this process, what we can say is like point-to-point network connection, a lot of disk I/O, a lot of network I/O. So this could be some real problem in a large-scale production cluster. So for the bottlenecks, we have done a lot of benchmarks here. Let's take two examples. The first one is using NWAIT, which is a graph computing workload. We observed that during the shuffle phase, we could see that the local hard drives here is easily become a bottleneck. The disk drives was fully utilized, and the latency, the RPS, is not going to satisfy the shuffle requirement. The other workload is Terraform, which is a common workload, I think, used by many of the big data engineers or admins to evaluate the cluster's performance. So for the Terraform, we can clearly see when doing the I/O phase, the CPU was not sort of used because the disk I/O was too slow. And when doing the sort phase, the CPU was almost fully saturated. So we are warning, we can come to a conclusion that the Shuffle is both CPU and IO intensive phase that need to be optimized. So let's take a look on what is remote persistent memory. IDC reported that the data is growing very fast. So the global data sphere growth rate is 27%, the compound annual growth rate. So that means the data is growing very fastly. But if we take a look on the DRAM density, it does not grow correspondingly. The growing rate is become more slower and slower. For now, it's like 4 years. Every 4 years, the DRAM density will grow 2 times. So there will be a gap between the memory subsystem and the data increase rate. So we need a new memory system to be met or close the gap. So with this, the industry is developing a new kind of a hardware. It's called a persistent memory. It's basically a new storage tier sit between the DRAM layer and the traditional storage layer. It offers higher capacity compared with DRAM, but at a slightly lower latency, but it's way too fast, way more fast compared with the storage layer. So it's trying to bridge the performance and operational and cost gap between the DRAM layer and the storage layer. So take Intel Optane persistent memory, for example. It supports 2 different operating modes. One is the memory mode, where you can use persistent memory as a DRAM, where the original DRAM was a cache for the PMEM. So from operating system's point of view, you will see a much larger DRAM capacity. The second URL model, we call it app direct mode, which it will be exposed as 2 different set of resources. One is DRAM, original DRAM, then the PMEM. You can have fully control on how to use these persistent memory devices. So it gives you a lot of flexibility to your applications. So the community is exploring how this persistent memory can be used. So typically in the big data cluster, we can use it in the following 3 scenarios. The first one is use it to solve the high availability issue. We simply plug the persistent memory on each physical node, and then the application will replicate the data in the local persistent memory across the fabric to another one. So in this is more like a purpose for backup or for high availability. The second use scenario is using the remote persistent memory to enlarge the compute node's memory capacity. So in this scenario, the application saw much larger memory capacity on the remote node. The third scenario is actually the most appealing one, where you using a pooled P-memory resources as a shared memory pool. So applications can share their data among the distributed pools. So in this scenario, it's the most interesting one the remote service was built on. So it looks like accessing the remote persistent memory will be the most challenging one. But because the persistent memory offers a remote persistency without losing any of the characteristics of memory, it's really fast, which means that you need ultra low latency networking. And it have very high bandwidth. It's like 2 gigabit or even 6 gigabit 2 gigabit for very small RAID and 6 gigabyte for large sequential RAID. So you will need a very ultra efficient protocol. The remote access must not add significant latency. Otherwise, it will have the bandwidth and the latency benefit you can get from the persistent memory. If we take a look on the right picture, RDMA offers moving the data between the 2 systems without involving CPU. It will offloading all the operations to the network for low latency. The latency is extremely lower, and it offers very high bandwidth. In today's most advanced network card is actually RDMA capable. The 200 gigabit, the 400 gigabit, it offers zero copy, kernel bypass, and the hardware offered one set memory to remote memory operation. It even offers a reliable credit-based data and control delivered by hardware, like the network resiliency and scale out. So this makes RDMA a perfect technology for remote memory access. But it does add some complexity. For example, because traditional RDMA, it does not take into consideration the data durability. So the CPU caches need to be bypassed or flushed to get data into the ADR domain. When writing to a person memory, it will need a synchronized acknowledgement when the write to have the made it to the durability domain. But currently, RDMA write is sort of like such kind of acknowledgement support. So to make it durable, today the solution is kind of based on the software itself. So take a look on the right upper picture. Actually, when the application trying to write to a peer RDMA NIC, it will need a RDMA read, a small RDMA read to force the write to the person memory. This actually makes the RDMA remote access not that kind of efficient. But the community, the industry is developing a new RDMA command opcode called RDMA flash. With this RDMA flash, it will flash all previous write to a specific region, and it will provide memory placement guaranteeing to the upper level software. So basically, we can leverage the RDMA flash to force previous RDMA write without another RDMA read. So this makes the person memory, remote person memory operation much more efficient. Okay, let's start to look at the remote person memory pool for Spark Shuffle. Let's take a look, recap on the first phase of this work. The left picture is the original Spark Shuffle, where a job serializes the object to an off-heap memory, and then it will write that to a local shuffle directory through the file system. And after that, the shuffle reader will read it from the local shuffle directory through file system and then send out the data through TCP/IP stack. So during this process, we could see a lot of user and kernel space context switch. We could see the file system was involved. It potentially can hide the benefit from the person memory, and the TCP/IP stack will be a lot of issue and consume a lot of CPU cycles if you have a Sovereign node, even tens of Sovereign node. To address those performance challenges, we developed the remote person memory extension for Spark Shuffle, basically like the red picture showing, where we serialize the object to the off-heap memory directly, and then position it to person memory using the user space PMDK library. So then we will read through the remote person memory through RDMA read. The RDMA memory region was combined, was registered as, with the person memory address. So during this process, because we were using the user space PMDK library, so there was no user and kernel context switches. And because there was no file system, we using the direct access mode, DevDex mode, to write to the PMEM directly, so we do not have the file system overhead. More importantly, we were using RDMA to read the data from the shuffle media and combine the RDMA memory region with the PMEM address. So this is a much faster implementation for the remote shuffle read. The result is actually pretty promising. We tested the performance with end-to-end workload, TerraSort, and decision support workload. For the TerraSort workload, we could see, compared with traditional vanilla Spark, the hard drive-based shuffle, the performance improvement is significant. And even compared with a full NVMe SSD as shuffle, we still see 1.29 times speed up. On the other hand, if we look at the read block time from Spark AUI, we could see a significant tail latency reduction between the different solutions. For example, the hard drive-based tail latency is 8.3 minutes. NVMe-based shuffle solution, the tail latency is 11 seconds. But for the PMEM-based shuffle, the tail latency is only 7 ms. So the tail latency has been increased dramatically. This is simply because the person memory provides a higher write and read bandwidth per node, and it has a much higher endurance and it has excellent latency because it sits in the DIMM channel. So the latency is much lower compared with the NVMe, which is attached to the PCIe bus. For the decision support workload, because the decision support workload is actually much less IO intensive, so we did not see such a big performance improvement, but we still see 3.2 speed up compared with hard drive based suffering. But if we take a look on the picture, the bottom picture, we could see that those IO intensive queries was accelerated dramatically, but the CPU intensive one was not that kind of much, which is with our expectation. So we already see this promising result. What are we going to do next? We observed some new challenges in the large-scale cluster, which is the disaggregated diskless environment. And people want to scale their SAFO with their compute node independently. And on the co-located cluster, the CPU and the memory was pretty unbalanced. And some jobs, they last for a very long time, for example, like 24 hours or even longer. So if the SAFO phase failed, they need to recompute the job again and start from scratch. The cost is almost intolerable for those users. So they were trying to develop an elastic deployment with compute and storage disaggregation environment, which definitely SAFO is a most important component in this new solution. So with this, there are requirements to decouple the side file from the compute node with a specific storage that is capable of delivering a dedicated service level agreement to different types of applications. So this will need to support fault tolerant in case of a SAFO failure, and so there is no need to recompute. It also requests to offload the data spill as well. So this will help to reduce the computer node memory footprint and improve the memory resource utilization, bring a much balanced resource utilization across your compute node and storage node. So because the traditional hard drive and even NVMe SSD, it might have the endurance issue for frequent write. So they want to leverage the state out of hardware as a storage media. So it can provide a high performance, high endurance storage backend. So those are the motivations that drive the intention to build a remote person memory with the fully disaggregated SAFO solution. So let's take a look on the remote person memory pool architecture. So basically, it's a new fully disaggregated SAFO solution that leverages person memory and RDMA technology. It will include three different components. The first one is the new SAFO manager. The second one is the person memory-based distributed storage system. The last one is efficient RDMA-powered network library that can bridge your Spark SAFO driver with the RPME distributed storage system. So for this Rtmp, it will provide allocate free read-write API on pooled P memory resources, which makes it easy to use and extensible. The data will be replicated to multiple nodes. For example, when the SAFO write to node 1, it will be replicated to another node through RDMA protocol for high availability. And because it provided those memory-like API, it can be easily extended to other unit scenario like data store, cat store. We can even use it as a cat layer for Spark. So with this fully disaggregated Rtmp architecture, it will help to improve the Spark scalability because it disaggregates the SAFO from component to an independent cluster. It will improve Spark SAFO performance because it leverages the person memory as a SAFO media. It also can improve the reliability in case of a SAFO failure because it replicates the data to another node in the Rtmp cluster. So if we take a closer look on the architecture side, we have multiple layers in the Rtmp pool. The first layer is the proxy layer. The proxy layer is actually built for the RTMP storage node to choose which storage to use. It was using a consistent hash algorithm to avoid a single point failure. It maintains active node map using the heartbeat to keep track on which node is alive, which node is down. So the the RTMP core layer it actually includes a three-layer design: the network layer, control layer, and storage layer. It will be in charge of replicating the data from worker node to a driver node of RDMA. Under the hood, those different person memory devices from different RPMP node formulate a global memory address space to the applications. Once the driver node goes down, the work node is still writable and readable because of the distributed design. So the RPMP client is provided a transactional read-write allocator-free API and put-get interface to user. The network layer is built on a library called a high-performance network library, which is based on libfabric. So it provides protocol agnostic support. It can be worked along with the Rocky RDMA, IWAP RDMA, or even InfiniBand. The RPMP server is a three-layer design, and the network layer have a HPR server running inside it, so it can talk with the HPR-based client from the client side. And the controller layer is responsible for the global address management transactional process. It also provides a set of accelerators, which can do sort merge, etc. The storage layer is actually responsible for allocating, writing the data to the person memory device directly. And it was using the user space PMDK library, so it bypassed the file system directly. There are multiple optimization features in RPMP. The first one is optimize the RDMA communication. As mentioned below, above, we were using high performance network library. It support multiple protocols. On the design, we actually leverage the server to handle all the write operations. We will have a server doing RDMA write to the client side on the read path. So this will avoid one-time RDMA communication. On the controller acceleration layer, we have the partition merge, which will aggregate small partitions to a larger one to accelerate the reduce phase, reduce the number of reducer connections. On the sort phase, we could even sort the software data on the fly. So there is no compute on the reduce phase. It will reduce the computer node utilization. It also provided a controllable fine granularity control of resource utilization if the computer node CPU resources is limited. On the storage layer, it have a global address-based accessor with a memory-like API. Under the hood is actually a key value-based store based on a libp memory object. So it is transactional, means that you do not need to care about the autonomy of your data, and the allocator for the manager on the person memory. A storage proxy will direct the request to different allocators. So each allocator will write the data to the individual person memory devices. So on the DTO workflow, we have a single node write and read workflow and a distributed mode write and read flow. On the single node side, the write data, the client will write the data. The client will be used by the software manager plugin. It will write data to a specific address. And then the server will issue a RDMA read from the client DRAM to the server DRAM. And then flash the DRAM to the person memory, and then send the ACK to the client side. On the read path, it will the client will read it from a specific address. So the server will issue a RDMA write from the server person memory to client DRAM directly. So in this way, we will notice that there was no DRAM involved. The data was fetched from the person memory device directly. Because the person memory provided memory like API, so it can be used as the RDMA memory region directly. On the distributed mode, it's a little different. When the data was write to the node 1's DRAM, it will issue a RDMA write to the second node, and so to replicate the data, and then the second node will flush the data from its DRAM to its PMEM. On the distributed mode, even on the read path, the second node will be not involved if the primary node was still living. So on the write to drive part, we implemented optimized pmemory shuffle writer based on the lib pmemory object. On the map phase, we will provision the pmemory namespace in advance. We currently leveraging a circular buffer to build a on-directional channel for RDMA primitives. We will serialize the data to an off-heap buffer, and once it hits the predefined threshold, it will create a block from through lib memory OBG, and then using a memory copy to write the data to the person memory. So this new implementation is append write, and only write once. So there will be no need for index files because we can saving the information in the lib memory OBG metadata. So this is lib memory based. It's bypassed the kernel, it's ultra efficient. On the reduce side, we're using memory copy to read the data directly, and we reduce will read through memory directly from RDMA. See, this is a brief high-level introduction, actually high-level summary of how the software manager looks like. We implement a pmemory software writer and a pmemory software reader. It's pretty much like a Hooker and the sort software manager plugin. On the beneath that, we support the block object writer and the external sort writer, which handle the software writer and the external sort directly on the write path. So the two different color actually represent on the right part actually represent two different implementation. On the up level, it's more Java based. On the below level is the CPP native code. So we will need some GNI wrapper on top of those native code to make calls to the lib memory OBG APIs. On the read path, the pmemory input stream will read the data from the Rtmp directly and then send it to a pmemory buffer and then send it to the pmemory software reader. We did some performance evaluation of this Rtmp solution. The left part is actually a micro workload benchmark. We simulate a client and server environment. We're using allocator, remote write and remote read micro test to test the theoretical or the maximum bandwidth of this Rtmp pool. We saw very promising result, especially for the remote read. We were able to hit the 40 gigabit network theoretical throughput. The right picture is integrating this Rtmp to Spark Shuffle. We only evaluate this prototype with 2 nodes, comparing it with the vanilla Spark Shuffle. In this configuration, we have 2 nodes, each have a hard drive based HDD as HDFS. And on the second configuration, the Rtmp configuration, we have 2 person memory on the second node playing the remote pmemory shuffle role. We could see in this prototype, we saw 1.98 times speed up of Rtmp based remote fully disaggregated shuffle solution. Okay, to wrap it up, we do see Spark Shuffle posed a lot of challenges in large-scale production environment, and a remote person memory is extending person memory new usage model to new usage scenarios with RDMA bringing the most advanced technology for remote person memory access. And the Rtmp pool for Spark Shuffle enables the fully disaggregated high-performance, low-latency Shuffle solution. It can improve the Spark scalability by disaggregating Shuffle from compute node. It can improve Spark Shuffle performance with high speed persistent memory and low latency RDMA network. It also improved the reliability by providing a manageable and highly available Shuffle services that support Shuffle data replication. So call to action. At Intel, we are committed to help you to accelerate your data analytics and AI journey by removing the technical barriers and inefficiencies. So we do not um, work on we do not only work on some single part. Instead, we start by enabling and building a modern, cost-efficient, scalable, and intelligent foundation not only at the hardware level, but also at the software level. So you could see from here we have a holistic end-to-end software solutions. We have libraries working on the hardware. We have the optimized machine learning and deep learning tools. We have also closely collaborating with the partners like optimized cloud platforms to provide a holistic end-to-end data analytics and AI pipeline to the end user. So the remote persistent memory is actually part of our big project called the Optimized Natives package for Spark, which include multiple optimizations based on Intel architecture and new most advanced hardware for Spark. We have the native SQL engine, which can help you to accelerate your Shuffle, accelerate your SQL query by leveraging the native implementation of the SQL engine and leverage the AVX512 instructions for more efficient data processing. It's column-based native processing engine. We have a remote Shuffle plugin and the Rtmp fully disaggregated Shuffle solutions. So if you are interested, feel free to go to this link and download and have a try. Yeah, thanks for attending the session. Do not forget to rate and review these sessions. Thank you.